You ever see a gnarly math formula and then look at its graph and just think, how in the world does that turn into this? Seriously, it can feel like some kind of magic. But it's not. And today, we're going to crack the code together. So we're about to go on a little adventure, from what looks like just a bunch of symbols in an equation to a real visual graph. Think of us as mathematical detectives. We've been given the clues, and we're going to solve the case of what this thing actually looks like. All right, here's our game plan. We'll start with the mystery, grab our tools, run the investigation step by step, reveal the final picture, and then wrap it all up with the big takeaway. Let's do this.
Okay, first things first. We have to understand the mystery we're trying to solve. Every great investigation starts with a person of interest, or in our case, a function of interest. So, meet our main character, this function f of x. But here's the twist. To really understand f of x, we first have to get to know its sidekick, this helper function g of x. They're a duo, you see, and figuring out their relationship, well, that's the key to this whole puzzle.
Now, before we just charge in, every good detective needs their gear. So let's pop open our mathematical toolkit and see what we've got.
This flowchart right here, this is our playbook. It shows us how to figure out what a function is doing at its most extreme points. We use something called limits to ask, hey, what happens when x gets ridiculously big or super close to 0? The answers help us find asymptotes, think of them as invisible boundary lines, and these branches that tell us where our curve is heading in the long run.
Okay, toolkit's ready. Time for the main event, our step-by-step investigation. We're going to follow the evidence, one clue at a time. Our first move is to put that helper function, g of x, right under the microscope. By finding its derivative, g prime of x, we can see exactly how it behaves. And the calculation here shows us g prime of x is always positive. That just means g of x is always increasing. It never stops, it never turns around.
And this leads us to our first huge clue. This is a big one. Since g of x is always going up, and we're told it hits 0 right at x equals 1, we know for a fact what its sign is. It has to be negative before it hits that 0 and positive right after. Let's lock that clue away. It's going to be vital.
Okay, now let's turn our attention back to the main subject, f of x. What happens when x gets unbelievably close to 0 from the positive side? Well, the math is pretty clear. The function just skyrockets up to positive infinity. And that gives us clue number 2, a vertical asymptote at x equals 0. Just picture an invisible wall sitting right on the y-axis. Our curve is going to race up right alongside it, getting closer and closer, but it's never, ever going to touch it.
So what about the other end of the spectrum? What's going on as our x value just marches off toward infinity? The work here on the slide shows that f of x also heads up towards positive infinity. But how does it get there? That's the next part of our investigation.
And this gives us clue number 3. When f of x divided by x gets closer and closer to 0, it means our curve has what's called a parabolic branch. The easiest way to think about it is this. The graph is heading up towards infinity, yeah? But it's kind of losing steam. It's getting flatter and just following the general direction of the horizontal x-axis.
Now, for the big connection, the aha moment. To find out when our curve is rising or falling, we need its derivative, f prime of x. And this is exactly why we looked into its sidekick function earlier. As we crunch the numbers, look what happens. F prime of x simplifies down to g of x over x cubed. The sidekick is literally telling the main character where to go.
This is clue number 4, and it ties the whole case together. The sign of the derivative tells us which way the function is heading. And since we now know the derivative sign depends entirely on g of x, we can use our discovery from clue number 1 to know exactly when f of x is going down and when it's going up.
All right, it is time to put all of our evidence together on the board. This is the variation table. It's basically the detective summary, taking all our little clues and organizing them to tell the complete story of the function's journey.
Let's look at this nice, clean version. It shows everything. Starting from way up at infinity, when x is near 0, the function falls because the derivative is negative until it hits rock bottom, its absolute minimum, at the point 1, 0. Then the derivative turns positive, and the function starts climbing again, forever, towards infinity. The entire plot, all in one simple table.
We've gathered the clues. We've analyzed the evidence. We have built our case. Now it's time for the grand finale, the curve revealed.
And there it is, the image we started with. But now, it's not a mystery, is it? Look closely. There's that vertical asymptote at x equals 0, with the curve shooting up. There it is, decreasing down to its minimum point exactly at 1, 0. And there's that slow, lazy climb up into the parabolic branch. Every single clue we uncovered is right there, plain as day. We didn't just find the answer, we built it.
So what's the big takeaway from cracking this case? Let's get to our final message.
You know, this methodical process, this step-by-step detective work, it isn't just for math. It's a really powerful way of thinking. Like the encouraging note in our source says, continue with the same determination. Effort always pays off. Breaking down a massive, intimidating problem into small, manageable clues, and then just following them logically to a solution, that's a skill that works everywhere. So the real question is, what complex problem are you going to break down next?